Hello, and welcome back to Old School Coding, where I'm using the language of the late 80s and early 90s to use the techniques of the late 80s and 90s to building a microcomputer that might have existed back in the late 80s and 90s. So yes, I'll be using C99. I am working inside Emacs. I'm using a make script to just keep building it over and over when things change. I am following some of the techniques that I used back in the time, and we are writing a signal level simulation for the 8080 CPU and some surrounding stuff, which we will turn into a real computer. By signal level, I mean that we are tracking the values of all of the signals that appear outside of chips and the state inside the chip that is architecturally visible, with the intent of reproducing timing diagrams. So what we see on the screen in front of me is our progress so far. We are very close to complete on the instruction set here, at which point we can start working on things outside the processor chip. We have 18 unimplemented instruction codes left, and that is return and conditional returns, the 8 restart instructions, and XTHL, which has an errata, and I will cover that last so I can verify that we're going into that very carefully and make sure everything is actually correct. Today, second session today, we are dealing with the return instruction and the conditional returns. Now, at this point, we still are in this test system where the ROM is shadowed in and we do not yet have a way to unshadow it. So all of our read operations, which include stack reads, are coming from the ROM. So our test system, let's start off by looking at the assembly code here. Let's take call test as a start. So ret test.asm. All these places I do a call, I really will be popping something off of the stack pointer. So what I want to do, the strategy that I'm picking, is we are going to have something ending at 100 hex. Actually, no, we will set this to stack bot. Just sbot. Now, each time we do a return or a conditional return taken, it will pop a word off of this sbot area. Okay. So it would return to the first byte there. So if the return's not taken, if I want this to work properly, I need to do the return not taken, and it needs to fall into a pop to get rid of it. So for call P, we're going to go down here, and the address I want to put in is call P. And this is just a ret. And very simple logic. If we failed, we're done. So this, call NZ F1, this would be a fail if it does the call. But I do want to put this in. So this is an RNZ. Okay. And if it didn't take it, then I do want to pop, let's say DE. So if I don't want to do the taken, I need to pop it off. We're going to sub C, and we're going to do an R and Z. This is going to be branch taken, so it should get to OK. There's the fail, and we get here. So this is our pattern. S-top. Stop. Actually, what I'm going to do here is I'm going to put in db s-top minus s-bot. This way I know how many of these I should be doing. And on the 8080, we do not need to align our 2-byte operations because this is an 8-bit CPU. The only 16-bit paths are the ones that are explicitly register pairs or are explicitly addresses. Okay, so what I want to do now is let's go through and change all of the conditional calls to conditional returns. And I will, while I am doing this, I'll use a keyboard macro to put the address down here on the stack. So we go into a CSC like that, and we say R, find the tab, grab that, go down here, DW, that word. There we go, have it. So call, and then to each of these. So this should be 17 words. So there's that. Let's make sure this actually assembles. Need to force a compile because nothing I was compiling before changed, and there's RET test, and there we go. So did I get the pops in that I needed? No, I didn't. So this is before all of these F3 locations. Which still, this label only exists because only exists because it was there in one of the other tests. So let's take a look. This is just this last one, spot checking it. Move A1, subtract C from it, and return minus. Not taken, so we pop the return address we didn't take. Subtract again, return minus, and we end up at CMOK, and our stack should be clean. So the other thing I want to do is when we're done, I do want to check the contents of the stack pointer at that point. Our stack pointer should then be equal to STOP. What's the best way of doing that? So there's a risk here. It is possible that the first time we do a return, okay, if we had sufficient bugs in the system, if this, for instance, instead of going from S-bot went to S-top, and somehow we got a hold on CMOK as our return value, we would pass this test without actually doing anything. So what do I want to do here? Let's actually do something that writes some stuff somewhere. Let's reserve 32 bytes there at log. So, yeah, that's not going to work. We don't have 32 bytes at log. This is already up to 62 hex, and we would have to put in code to include it. See, can I do it? I could do it above here. Let's say org 00C0 hex. And let's set this, well, let's give us more space if we need it. Okay, if we don't need it, we don't need it. So I'm going to use HL to point to my log area. And B is going to be a counter. What I'm going to do here is I am going to mov m comma b. So that will be my thing to confirm we've got something. Actually, let's do it even one better. It's mov m comma l. We'll do that before next subtest. This is exceedingly paranoid. Now, as it turns out, this log that I'm writing, I could put this at 0 because I am reading from the ROM, right? So I'm writing to this log area, which could go anywhere. In fact, it could even go at 80 hex. But let's not. Let's keep it where it is. So we're not overlapping. So if we were to copy this into a RAM and run it, it would still work fine. And here we want to set just reserve some space for it. Because it's going to write to RAM, we're going to pre-initialize the RAM. There we go. So there is our test program for return and conditional return. And now if we were to actually run this test program, we would simply hit the instruction not found thing. Well, let's test that. .8080 underscore test.c. And we need i8080 underscore ret.c to look just like call.c. Test the call and conditional call instructions. Test the ret and conditional ret instructions. So set the RAM.own pattern, run the test program, check that bytes are changed. Here's all the boilerplate. So yes, there's still a little bit of boilerplate here because we're not just running the program, we're also testing stuff at the end. We are still within 256 bytes. 5A is still a good value. So if we skip over subtests, this will still have the same pattern. It will just be short. So if it's short, we won't know which test we skipped over. But that's easy enough to fix later on if it turns out to be a problem that we want to worry about. There we go. Again, we are not looking at ROM during this part of the test cleanup. There we go. And I-8080 test. Let's go to inc first. Everywhere we have call. No, not everywhere we have call. Flags, impl. Really, call should be down here. Opcodes, phases, status, test.h. Declared. So if we immediately turn on our test, we see that we start right out with, we have an unimplemented instruction that we're hitting. C9, C9's call. So that's correct. We're hitting the unimplemented instruction. So here, now we start implementing. Okay. Change the C's to R's. Not for CC, though. That's condition code. Now, all of this is going to change. For instance, we no longer have the whole M2, T3 thing, M2, M3. So let's go wipe out our stuff. Let's take a look at our PDF first, though. Now that we're getting to looking at the instruction stream, I didn't start the PDF yet. So we are looking for the RET instruction. View 2 pages with cover page. I was RET, where would I be? I'd be on the second page, wouldn't I? So RET does nothing in T4. RET with condition judges the condition in T4. We then, notice here, judges condition in T4, RET with condition is, if the condition is not met, cycles M2 and M3 are skipped. So RET not taken judges the condition and dumps right back out into normal M1 T1. I don't know why they... Oh, okay. So, yeah, they repeated these cells because there's one in the middle where RST does something slightly different in Phi3 that captures the N into the W register. But we can handle that easily enough. So judge condition will maybe do nothing, like jump. Well, jump has an immediate. So we are pretty much RET is just like a call, except there's no immediate, and we're fetching from the stack rather than pushing, or popping from the stack. And the M2 cycle is going to be send SP, increment, read. Send SP, increment, read. So these are like pops. So this will look very much like a pop into SP, but it's going to go into WZ and then get committed to PC at the end, just like the other branch instructions. I didn't turn that on, did I? Here we go, PDF. And this is what I was looking at here. So RET on this line, T4 does decode, T5 and T6 are pops, and at the end of M3, let's see, M2 and M3 are pops, and at the end of M3 we're going to take WZ and toss that into the PC for us. Condition return does the condition judgment in here, T4 and T5. It then does the pops and either branches or not. Well, if it does the pops, it's going to do the branch. So yeah. So that's what we've got. Let's do the RET logic first. So RET M1 T4 does not have it at T5. We do have a RCC M1 T4 and RCC M1 T5. Now previously what I did was I had an R naught like that. And those will come from macros. And we've got those up here. RCC M1T4. RET M1T4. The existing M2 and M3 go away. So what I'm going to do now is search for M2 and M3 and get rid of them. There we go. So M4 and M5 become M2 and M3, and they change from pushes to pops. Now there is no of those. So if the branch isn't taken, we have an M1T5, which does the appropriate thing for branch not taken. And if branch is taken, we do need to spend that T5 cycle. So we do have a RET. Now, I believe that what we're doing here in the second state T5 of the conditional RET could just be the same as the state T4. So we are going to say conditional RET taken uses M1 T4 during T5. So there's our logic. Okay. And now we need to begin implementing. RET M1T4 does nothing but set the next T-state handler. Just like that. Now the conditional RETs are going to evaluate the condition, and they do nothing else. They do not set IDAL, so we can keep our normal behavior from everywhere else in the system where state next is in phi2 fall. And if we are taking it, we're going to jump back and we're going to do this guy. We're going to spend one T state here in T5 because that's the timing of the 8080. We don't need to. I mean, looking at RET, it really, RET condition takes 2 cycles to judge the condition. Come on, guys. I don't know what's going on inside the 8080. Maybe it just does take that long. Okay, now we implement those for the various flags. Flags RY. Remember we had that underscore C? There we go. So continue on downward. The next error is way down below R0, M3, T3, and so on. So RET M1 T5 doesn't exist. So RET M2 T1, this is not a push, this is a pop PC low. This is a status S read. Oh my, somebody wants to come look at the code. You ever have a manager who demands you do a code review in the middle of work? That's what I've got now. Okay, Lucy, so what have we got here so far? You're not looking at the code. No, you're not. So coming in, we have a T-state handler established that will pick up our return instruction. And it really does nothing but control where we're going next. You settling in? You settling in, okay. Now she's looking at the code. So we have a separate M1T4 for each of these instructions. A normal RET simply says start a fetch from the stack, a stack pop, an M2T1 style stack pop. And the conditionals will say, check the condition. If the condition is true, then the T5 will look like the M1T4 here. And if it's false, then we'll hop down into the R0 M1T5. Okay. Implement that for each direction of each of the 4 flags. Done. So now we get into the adder sync cycle for popping PC low. So SP goes out on the address bus via IDAL, and we get a stack read, and we raise sync. And that goes to M2T2. This is, I believe we increment SP here. Let me make sure while I've got the cat on my lap. Yep, we need to increment IDAL and put it into SP. Is that right, Lucy? Yeah. And this is a read, not a write, so we are not doing dset. Editing code with one hand is probably risky. I will give her a little bit more time on my lap. So we're just going to come back through here after the cat gets down and go over everything. Let's plan it out though. So this is a pop PC low that we're going to do here, and it will increment the stack pointer. And then the T3 part of the cycle is where we are going to commit that data into the, checking real quickly on my notes, into the Z register. So the writes are going to go away. We're going to get a DB in there. We're going to release DB in. M3T1 is a pop PC high. We will edit that when the cat decides to get down. Pick up SP. Add a, go into there. M3T2, we need to commit back the updated SP. And that's going to go away. M3T3, again, red M1, the WRs go away, and that is complete for return taken. Now for not taken, these guys go away because we don't have to do anything with immediates. And this goes away because all we're doing in this guy is doing this one thing here. There. So I'm going to see if I can interest this cat in sitting under a blanket because she's trying to go to sleep. I'll be right back. Okay, back to the top so we can do the edits we just talked about. So M1T4 launches us into the pop cycles. This launches us into M1T4 or into the end of world. Pop low, raise sync, lower sync. We now need to pretty sure that's the incantation. Okay, I've got the stack pops over on the right-hand side so we can compare them. DSET, status SRead, check. Raise sync, check. Lower sync, detry data, raise dbn, and this is where it's incrementing SP back is here. Oh, and I almost forgot I need wait states. So T2 needs a TW. As does M3. And I need to terminate my test program, which is now running infinitely. And which has spewed infinite amounts of data into my Emacs buffer. Emacs may be crashing at this point. Yes, it is crashing. Yeah, Emacs doesn't like it when you hand it hundreds and hundreds of gigabytes of text output. And I did let that just kind of spew into that line, that area for a long time. Get this set back up. So you don't see me start with a blank editor much. So yeah, the code is running infinitely because I have no safety checks for that. Back to what we're looking at here, and I'm going to go into source AD stack.c for the pop implementation. So M2T1, cross-checking this, we have set ADAL, set adder, data sync. Next state. Next state is T2, where we have lower sync, tri-state data, raise DBN, increment SP. And then we have if val ready, yes. And then we need a wait state here. So this is the inc SP cycle for pop PC low. The wait state, much simpler. We force DBN to be 0 and then increment it. Let's put the comment in properly. At the end, we repeat the val ready check. So if we're ready, we go to the M2T3. If we're not, we stay here. Note that we don't even need the else clause there because we're not changing state. So T3 finishes it off. We lower weight. Whoops. Almost forgot to raise weight there. Lower weight. Need to make sure that we write into Z register. So this is dset Z. Now M3 is just like M2 with changes because it's the other byte and because we need to commit at the end. So the M3 we're popping into PC high, which means we're capturing into W. And phi2 of the final state, we do the same thing as jump. We just bop that right in there into PC from WZ. And now I'm going to start my build loop going again. It didn't run forever, yay. So, state RET M2T2 is redefinition. M2T1, M2T2. This is M2TW. And that's still running the old binary, which runs forever, so I need to do this quickly. 3TW. There we go. Still running forever. So let's check state next. So M1T4 goes to M2T1. M1T4 conditional goes to M1T4 or M1T5. Not. M2T1 goes to M2T2. M2T2 goes to T3 or TW. M2T wait goes to M2T3. I'm going to put in the else clause just to make absolutely certain that it should be redundant, but maybe I made a mistake. 2T3 goes to 3T1. 3T1 goes to 3T2. 3T2 goes to 3T3 or 3TW. 3TW, I'm going to do this again. 3T3 or 3TW. And M3T3, forgot to raise M1 int. I think I've been lowering weight before that. And not raises M1 int. Okay, so M2T3, did that one forget to raise weight? No, it didn't. Raise weight, lower weight. Raise weight, lower weight. There we go. Check weight. So raise it in TW, lower it in T3. Raise it in TW, lower it in T3. There. There we have it. So now the test condition is failing because in the comparison, I saw that somebody had the wrong value. The observed value was C0, and I was still testing for that. I think this ran. I think what I'm going to do see what that says. So C0 through C8, so that's 9 of them. That's 202, 203. Why is this not printing peaks on any of these? Oh, her to her, RAM test area. There. There we go. I just have to add 9 instead of 11. There we go. And that's returns. So we can't really do calls and returns together until we have the return from interrupt, or not the return from interrupt, until we have the turn off shadow thing. I'm going to call it for today, since these two sessions together are adding up to as much as I want to do today. What do we have left? We have 9 unimplemented instruction codes, which are the 8 reset instructions, which are just calls. Oh, I could do the RST calls. I could do the RST calls. Yeah, I think I am going to do that. I believe I have this adequately commented, so I can just push this. Do I have it get cracking running? I believe I still, nope, it got killed. Okay, so, oh, I still need to put the image links in there. Hold on. Live coding test I8080 ret test.c. So there should be a bist underscore ret. I don't see bist ret in there anywhere. As in bist. Timing. I bet you I've made a trivial goof. No, I am using the next subtest stuff here. Well, there's the CC output for it. Go down to timing. There is no timing data logged for RET. I-8080 as in BIST. Jump IO Mavum stack LDST call. Ah, got it. Hold on. I-8080 test.c. Call. So we got into RET post, but we never got into RET BIST. Same logic, but we never did the BIST, so it never actually did it for us. That's better. The only difference between post and BIST for us is whether to do a plot or not. And there's our RETs. So RET1, here's a normal RET. Let's bring up our LST file here. So this first bit, LXIHL, yada yada, get all set up, and we eventually do a C9 instruction here. W is briefly set to Z and W, and that takes us right along. The address bus 0, 1, 2, 3, 4, 5, 6, 7, 8, 81, 82 is our pop, and A is where we end up. Okay. So the others should look very similar. Okay, good enough. So just like I had those files for images for RET, for call, I now have the same thing for RET. And there's our figures for RET right there. Working around with Git just a little bit. Make sure we are absolutely clean before I do this. And make loop. And run report. We are not clean because I still have those stubs set. Oh, cat's back. Where is she?
She's right there.
Oh, okay. So she sat under the tent for a little bit, and now she's in the bedroom door saying, is somebody going to come to bed? It's not bedtime, cat. It's 5 p.m. Anything else I need to check in? I think we're good. Okay. I'm just going to commit for the shell. This is add RET and conditional returns. Push. So RST is a little more tricky because RST is going to branch us to those various locations. RST0 is going to start us over again at 0. Somehow I need to be able to tell the difference between RST0 and when we come out of reset. When I can't store anything to memory and recover it. Let me do an initial state. Right. So carefully crafted initial state. Let's do the implementation first. We're not going to really look like anything except maybe I-8080 call. We're actually calls where the address is implicit. We don't have the flags because we are not doing any conditions. So, PDF file time. RST is this instruction right here. So, during T3, it picks up something into W. It says phi, but over here, temp equals 00 NNN 000 goes to Z. Oh, this is 0 goes to W, so they have a 0 with a slash through it. Not understanding why they have a 0 with a slash through it there when all of the other zeros are normal and where they used phi elsewhere. This may have been an error in transcription. But we can take care of 0.w anytime we want. So during T4 and T5, we're going to be incrementing the stack pointer. So this is going to look a lot like a call. We're decrementing the stack pointer. Pah. Right, so we look a lot like a call. And I am going to, I will pull those 3 bits out of the IR when it comes time. Okay, so there's probably enough boilerplate in call that I can just do it. So call M1T4, call M1T5, change call to RST. T4 and T5 take care of decrementing the stack pointer. Comments on the right just to remind me what it's doing. And I am working behind the PDF here. Okay, so RST does that. M2, T3, M2 and 3 go away. Again. So we're going to continue chasing down M2 and M3. We don't need anything to do with condition codes. We don't have anything to do with the C naught. Okay. Now we change M4 to M2 and M5 to M3. And now we write the code. So still operating on the mixed environment where I've got the PDF up. I need to remember that I'm doing that. So RST, during M1T4 and M1T5, we are decrementing IDAL. Got it. There's that. Now we go down to M2, where we are starting a push. Same as before. literally. I don't think I'll need to change this code. Let's check it though. SP into IDAL, out to address, stack right sync, bump to next. Drop sync, put the high byte of PC out on data. That's correct. Decrement SP here. Checking that. Yes, we do. M2T3 is the right cycle here. Head into M3T1. SP into IDAL. IDAL into adder, stack right. The T2 comes out, drop sync. We set the data. We do not decrement SP again because we've already decremented twice this instruction. RST, that's a check. And then during M3T3, what we are going to be setting here is val of IR amper OX. It's the hex value, octal value 0070. So this is OX38. It is probably not coincidence that the bits in the instruction specifying the offset are aligned the same as the bits in the actual thing. Now this actually, if we want to make it work just like the real one, we need to do a D set into Z, and then A set P, that of RP of WZ. Now W equals 0 was all the way back here in M1T3. We're going to do it in M1T4. So it's probably doing that because we're going to be messing with SP during T4 and T5. And writing to W is going to use that same data bus that goes through the register bank. Which means that clearing of W has to happen as we are bringing the instruction in to the IR. I also noticed that when the instruction comes in, we're being told it goes into temp and IR, which works because out here, if we look at the RST instruction on the late clocks, it's using the value in temp, not the value in IR, to determine NNN. Now that makes sense. So let's take the performance hit. So we're deset IR. We also want to deset TMP. So temp is always going to get the opcode. And here, there. So M3T2 is calculating temp register, and M2T3, it puts it on Z, and PCL goes out on the data bus. Okay. And our little A set of the PC here, D try of W and Z are going to happen after that. I like the idea of setting the PC during this last possible instant because it really doesn't happen in the real hardware. And we want to delay that sort of thing. So we did that during jump. And we did that during RET, so now we just need to make sure we're doing it here. So now, let bin loop go, and let's let report go. And this says that RST M2T1 is not being used. Well, that's because this guy is directing it to 2 bops. So I do have to wonder how we were getting control back to get this test passing. Oh, we're not testing RST yet. So sometimes I write tests first and sometimes I don't. And I'm beginning to see why people would be motivated to just put a flag in the ground that says always write tests first, even though it's sometimes counterproductive, because if you start making mistakes like I am, and you may come out with, I'll write the code first, and then later you're done with the code, and you think you've done the test, and you haven't. And one way to do that is, for a final check, you put a bug in the code and see if the test catches it. Well, that just triggered for me. So how do we want to test the RST stuff? Initial state before start. You know what I think I'm going to do? I think for RST, I'm finally going to implement something that turns off shadow. No, that's more than I want to do right now. What that would involve would be when we get a reset, we're executing in ROM. The ROM code would then jump up to its normal location, turn off shadow, copy ROM to copy the program into RAM and run it. And that's a little more than I want. Initial state before I start, HSP. I'll call this vec0, vec1, and so on. So coming out of reset, So if I just did that, we would loop infinitely, right? So now I need something so that the second time I hit here, I can be done. Well, maybe not the second time. Aha, I know what I can do. If I set my flags, I can do an immediate branch. So set the flags so that the flags are basically no flags are set. I'm going to do a JZ to done. Each one of these I'm going to say, oops. No, start with a equals 0. To do this test, start with a equals known value. I've got 8 bytes to worry about. This is 2 of them. Okay, so for this first guy, I'm just going to jump out here. And he's either going to RST7 to start the test off, or he's not. So I am going to collect 1 bit per test vector. Now let's do it the other way. Now I do need to test RST0, don't I? No, what I think I'm going to do. I think I'm going to call it a stream. I'm going to go think about how to test the RST instructions without coming out of shadow mode. And I will probably cover that test program when we come back, because all we have left to do are the RST instructions and XTHL. So, and I've been doing all that coding behind the PDF, but that's okay, because this coding that I've been working on is absolute dog crap. So I will talk to you then. So until then, keep it small and keep